everyone, and happy Friday. Welcome to the Tejano virtual event Happy Math Hour, our weekly interactive math reviews for Math 1314 and for Math 1324, which are presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need to, and so that others who've missed today's event will be able to come back and watch it also. So now at this time, please mute your mics for best sound experience. Otherwise, the feedback could interfere with information that we will be sharing. If you are here for the Math 1324, I'm going to go ahead and post let me see. I'm going to post a link so that you can go ahead and connect with the Math 1324. We also will be sending individual messages to everyone so that we can gather your student ID numbers to sign you in. And now, without further ado, I'll pass it over to our presenters so that they may begin.
Again, good morning, everyone, and thank you for joining us on this Friday. For today's session, we're going to be doing synthetic division and complex numbers. But again, before I start, again, if any of you are here for the Math 1324, you'll find a link on the chat. Go ahead and click on that link, and that will take you to the 1324 Happy Math Hour session. Okay, so the rest of you who are here for Math 1314, go ahead and let's get started. So we've covered this section before, but um, let's suppose that we have this function 6x cubed minus 19x squared plus 16x minus 4. And if we were to factor this out, we would be able to find our zeros, right, or our solutions of our graph, or our x-intercepts of the graph, right? Um, and sometimes, the functions are easy to either factor out or simplify to be able to get these zeros, but sometimes it's not that easy. So that's where um, division is going to play out. So division of polynomials. First, we're going to see this thing called long division. Okay, um, and what this process is going to allow us to do is going to allow us to simplify polynomials into where we can either factor them or find the actual solutions right away by doing this process. Okay, so to do long division, we came up with some steps to help you do this. Okay, now, and it's very similar to regular division. If you guys remember how to divide on paper regular numbers, the process is the same for polynomials. So the first thing that you need to do, and it's very important, is to arrange the terms of the dividend in descending order powers, and also of the divisor. Okay, but what does this mean? Okay, so that means that the numbers that go inside the house have to be in their proper place value. And descending order powers means that the highest exponent goes first, and followed by the next highest, and so on and so forth. Okay, so that's what it means in descending order. And then you're going to divide. So if you remember to divide the first term, um, we have to find a multiple that will get us close to that number, if not that exact number. Okay, and that number that we're going to multiply, that's going to go into that first dividend, goes on top of our house, which makes part of our quotient. Okay, so again, once you've multiplied, you write the resultant on the top, okay? And then the multiplication number goes below the number, and then you subtract, okay? You subtract the product of those two numbers. You may have a remainder or not, but then what follows next is you bring down the next term that, as in our dividend, you bring it down, and then you do the same process again. You try to find a multiple, you try to find a number that you're going to multiply with your dividend that's going to get you that same number inside the house or very close to it. Okay. And again, when you do that, you you put that number on top, which is part of your quotient. You subtract, and again, you follow the same process until you have no more terms to bring down. Okay. All right. So the best way to see something like this is let's just look at a visual example of it. And again, we're going to first start with log division to divide these two polynomials. So I have my um, my dividend here is 12x cubed minus 35x squared plus 23x minus 6 divided by my divisor, which is 4x minus 3. Okay, so the first thing that I need to see is my both my dividend and my divisor. I see my divisor is already in descending order. I have the highest exponent is a 1, and then that 3 is a constant. So that one's okay. And also my dividend. My dividend is also already in its particular order. The highest degree of this polynomial is a 3, so then it's a 2, 1, and a constant. So it's in descending order, okay? So now we can go ahead and divide. So again, just like before, like I was mentioning to you, the way we divide polynomials is the same way we would divide numbers. We would put our divisor outside here, and then we would do like a little house, and our dividend would go inside here. And it's already in the proper order. And it's important because it's a placement value, okay? All right, so let's go through the process. Um, I say to myself, what can I multiply to 4x minus 3? Or basically just this first one always. What can I multiply to 4 that can get me close to 20? And what can I multiply to x to get me an x cubed? So what that value is here, if you don't see it, you can divide these two numbers together, right? Or these two terms together. 20x cubed divided by 4x is 5x squared. So that's the number that I want to multiply to my 4x. So that's what I'm going to do. And again, I'm going to put that on top of my house. Okay. So I have the 5x squared on top. Now I'm going to multiply. So it's a polynomial. I'm going to have to multiply this 5x squared to both the 4x and to the negative 3. So let's go ahead and do that. So when I do that, 5x squared to the 4x gives me a 20x cubed. 5x squared times a negative 3 gives me a minus 15x squared. Okay, then what comes next after division? We're going to subtract, but we have to be very careful. We are dealing with polynomials. So that's why we put this blue parentheses here, because this negative symbol or subtraction, I need to distribute to these two numbers. So once I distribute that negative symbol, negative times a positive gives me a negative 20x cubed. A negative times a negative is going to give me this positive 15x squared. So now I can add the two polynomials, right? So I'm going to add 20x cubed minus 35x squared with this negative 20x cubed plus 15x squared. So when I do that, I have 20x cubed minus 20x cubed is 0, minus 35x plus 15x squared is a negative 20x squared. Okay, that was what was left over of my subtraction. Then I'm going to bring down the next term, the 23x. And then I start the process all over again. I repeat it. I need to find a number or term that I'm going to multiply with the 4x that is going to give me a negative 20x squared. Okay, now what is that number? Again, that number is a 5. A negative 5 will give me a negative 20, and x times x is going to give me that x squared. So this is the term that I'm going to multiply. So then I did it again. I multiplied the negative 5x to the 4x, giving me the negative 20x squared. The negative 5x times the negative 3 is a positive 15x. I subtract, but it's a polynomial, so I'm going to distribute that negative. So when I distribute that negative, a negative times a negative is a positive 20x squared. A negative times a positive gives me a negative 15x. And then add negative 20x squared plus 20x squared is 0. And then we have 23x minus 15x gives me an 8x. And then I bring down my last term, the minus 6. Okay. Then I say to myself, what can I multiply to 4x that will give me an 8x? Well, that's a 2. That's a positive 2. So if you see, I'm putting the sign of what I'm putting here, right? So I have a positive 2. So plus 2 times 4x gives me a 8x, plus 2 times a minus 3 gives me a negative 6x. But again, I'm subtracting. So a negative with a positive is going to give me a negative 8x. A negative times a negative is going to give me a positive 6. And I have these the green lines in blue. So now when I add these two polynomials, I see that my remainder is 0. Okay? And I'm done. This is an example of long division. And what you see here is we broke up this big long polynomial. We had a cube polynomial and we divided by this 4x minus 3. And if I would multiply my divisor with my quotient, I would get back my log polynomial. But you see that if I wanted to find the zeros of this polynomial here, now it becomes easier because I can find the zeros of this one, which is a linear, very easy to find. Just set the y value to 0. And then on this one, we have a quadratic. And again, we have a lot of stuff under our belts now that we can use to solve a quadratic. We can use a quadratic equation, our square root property. We can factor, right? So it's going to help us to find zeros better. Okay, so let's look at another, just to review what I just found. Okay, so again, the number outside here is called my divisor. The answer that I have here, or the numbers that I was multiplying to get to a remainder of 0, is called the quotient. Okay, so and then sometimes we're not always going to get a 0 as our remainder. Okay, and I'm going to show you how we handle that as well. All right, so and here's an example of how we would write it in case we had a remainder. Okay, so if you guys remember, with dividing regular numbers, if we ever had a remainder, you would put plus whatever the remainder was divided by your divisor, right? This is how we had the fractions or the decimals. There's nothing different with our polynomials. The way you're going to write it is we're going to do plus 0 was my remainder over the divisor. My divisor was 4x minus 3. So this is the format that you would write in case that you had a remainder. Now, again, we put it on here for right now just so you can see how the answers are supposed to be put in on your homework in case you do have a remainder. But if you just put 5x squared minus 5x plus 2, the homework is going to be correct. Okay, it's going to be marked right. You don't always have to put like this. Now you can put it if you want to. Okay. All right. So that was an example of long division, but a faster way to do division, and I think it's a little bit clearer, and it's good to practice because sometimes we want to divide to find out to see if we have a factor that we're always going to get a remainder 0, and we don't want to do long division all the time because you see it's a process. So synthetic division comes to our help to do these divisions a lot quicker. Okay, so again, it's like a shortcut of long division. But in order for us to do synthetic division, our divisor always has to be in this form, x minus c. If our divisor is ever has a square or something that's not linear, we cannot use synthetic division, okay? Our divisor always has to be in a linear fashion, okay? All right, so let's look at this. So these are the instructions to do synthetic division. Okay, so if I'm dividing a polynomial, again, my divisor has to be in this form, x minus k, and I'm using these variables because these are the variables that your book uses. Okay, it's almost as similar as the long division. First thing we need to do is we have to make sure that our terms are arranged in descending order by their degree. Okay, then we have to identify the coefficient of each of our terms. And if there's any terms missing, we have to put a 0 for that coefficient, okay? Because we have to have a placement value, okay? It's not like our long division. We don't have to worry about that. But on our synthetic division, we have to worry about our placement values. Yes. So then the last step is we're going to write the k. Okay. Again, only the second part of our coefficient um, as listed below. So here's a generic example of how we're going to do synthetic division. Okay. K is from my divisor. The A, B, C, and D are the coefficients of my polynomial. So let's say that my polynomial is this one, ax cubed plus bx squared plus cx plus d. These are only the coefficients, the numbers that are in front of the variable x. Yes, please do not write any variables for synthetic division. All I'm writing is the coefficients. So, and if you see here for for synthetic division, our house is now upside down. Okay, and it's for a reason. The first step that we're gonna do in synthetic division is we're gonna bring the a down. Okay, and then after we bring the a down, we're gonna multiply it with the k. And once we multiply with the k, we're going to put it underneath the b here. So this would be ka over b. So then we are going to add these two numbers because they're just going to be numbers. We're going to add those two numbers. We're going to get the b plus ka. Then going to do the process again. We're going to multiply k to this answer, b plus ka. And then I'm going to put it here under c. And then I'm going to do the process again. It's going to repeat. I'm going to add c with this product, and then I'm going to get an answer, and then I'm going to do it again. I'm going to multiply k. So then now that answer, it's going to go below the d. And since d was my last coefficient, which was my constant, this last circle is going to give me the answer of the remainder. Okay. So this last bubble here is my remainder, and this part here is the coefficients of the quotient. Okay, now remember when you are dividing, okay, we're simplifying. So for instance, if this polynomial was a cube polynomial, my quotient here, this a, is I lost a degree. It starts now with a square. This would be ax squared plus bx plus c. Okay, and then the last one would be my remainder. Okay, so keep that in mind. But the best way to see something like this is let's go straight to an example so you can visually see it. Okay, so again, first thing that I need to do before I think of anything, I need to make sure that both my divisor and my dividend are in descending order. Okay, and it is. My dividend, it has a degree 2, 1 constant. It's imperfect. It's in the right order. My divisor is also in descending order. I have 1 and the constant. Okay. Now, what is my k? So if I see here, my k here is 1. Yes? If you remember the formula is x minus k. So my k is a positive 1 because the sign here is still negative. Now, if the divisor would have said x plus 1, then that means that my k is a negative value, and that's what made the negative with a negative become a positive. So here my k value is 1, and I put it out here. The next thing I do is I'm going to list the coefficients, okay? So all I'm putting are the coefficients. So my coefficient here for the x squared, we don't have the number here, but we know that there's 1 x squared. So that goes 1. Then we have a 5, and then we have a 6. 6 was my last one, is my constant. Now I'm ready to do the synthetic division. First thing I'm going to do is I'm going to bring down my 1. 1 times 1 is 1, and I'm going to put it right below the 5. Now I'm going to add these two numbers, 5 plus 1. 5 plus 1 is 6. So now I'm going to multiply 1 times 6. So when I multiply 1 times 6, that gives me 6, and I put it again below my last coefficient. So this is 6 plus 6 is going to be 12. Okay, so what do I have here? 12 was my remainder. This wasn't 0. I had a remainder. Okay, this portion here was the dividend, which was the x squared plus 5x plus 6, right? But this was my divisor that came from the x minus 1, and my quotient now is on the bottom. This is my quotient, the 1, 6. But again, we lost the degree because we did division. We simplified this polynomial that was a square, now we have something that is linear. And the way we're going to write it is like this. It's the quotient plus the remainder divided by the divisor. So in my case, the 1 belongs to just the x. The 6 is now my constant, plus the remainder, which is 12, over my divisor, which was x minus 1. Okay, this is how we do synthetic division. Okay, let's see. Let's go ahead and do another one using synthetic division. Okay, first thing I need to do before I start the work are my polynomials in descending order. Let's look at my dividend. I have a degree 3. That's the highest exponent, so I have a 3, 2, 1 constant. Perfect. It's in the right order. My divisor is also in the right order. It's I have a 1 and a constant. We're ready to go. So the first thing I need to do is, what is k? My problem here, k is the value 8. So that's going to go outside the house. And now inside my little upside down house, I'm going to put in all of the coefficients. I have 4, here we go, 4, 36, 36, negative 32. Okay, synthetic division. Let's go ahead. Break down our 4. 8 times 4 is going to be 32. Add 36 with 32. This is a 68. Now multiply 8 times 68. That gives me 544. Add 36 to 544. That gives me 580. Now multiply 8 times 580. That's going to give me 4,640. And add now negative 32 with 4640. I am going to get 4,608. Okay, so again, this last number was my remainder. I started with a cube, so my quotient here, this first is going to be a square, right? So what I'm going to do is have 4x squared plus 68x plus, this is my constant, 580, plus the remainder, which is 4608, divided by my divisor, which was this x minus 8. Okay, so again, it's a quick way to do division, right? Using synthetic division compared to long division. Okay. All right, let's do another example. Again, we always want to check if everything is in the right order. And look, my dividend here, my highest degree or my highest exponent is a 3, but this guy is not in the right order. I have a 3, then a 1, and then a 2, and then a constant. So it's a little bit of fixing. The second number should be the 21x squared, or the second term, and then minus 6x, and then minus 42. So let's go ahead and do that. When we put them together, we notice that we need to put them in order. Okay, so I've done it. Now it's in the right order. 3x cubed plus 21x squared minus 6x minus 42. But then the other thing to notice, there's a plus 7. And the formula says that I have to have it in x minus k. Again, for this to be a plus, then that means that my k was a negative 7. Because a negative 7 with a negative symbol is going to give me that positive symbol. So then again, my k will be that negative 7. Yes? So now what goes inside my upside down house is all of the coefficients. Now that they're in the right order, it's 3, 21, negative 6, negative 42. Okay? Be careful with the signs. Make sure you carry the sign of the term because then things won't go well. Okay? All right, let's do it. First thing I need to do is I bring down my 3. I'm going to multiply negative 7 times 3. That's going to give me a negative 21. 21 minus 21, that's going to give me 0. Now, negative 7 times 0, that's 0. Add negative 6 to 0, that's just a negative 6. Now, negative 7 times a negative 6 is going to give me a positive 42. Negative 42 plus 42 is 0. Okay, and that makes us really happy when we have a remainder of 0. Okay, because that means it makes the polynomial simplify completely. But anyway, we'll get to that. So again, my answer here, I started with a degree 3 of my dividend, so it lost the degree. So now my answer is 3x squared. Again, you don't have to put this, but just so for explanation purposes, the next one would have been the 0x. There's nothing there. Minus 6, that's my constant, plus 0 over x plus 7. Again, there's no problem if you put this answer on the computer. It's going to mark it right. But we can simplify it because 0 times x is just 0, and 0 divided by anything is just 0. So my quotient can really just be written as 3x squared minus 6. Okay. All right, let's do one more. I'm going to use synthetic division. Again, do I have everything in the right order? Let's see. My highest degree is a 3. I have a 3, 2, oh, I'm missing one. I should have an x term and then the constant. My divisor is in the right order. So on this one, not that it's not in the right order, it's just missing a term. So in order to compensate for that, I'm going to put a 0x on my polynomial. Okay. So what the first thing I'm going to do is I'm going to rewrite my polynomial this way. X cubed minus 3x squared plus 0x plus 6 divided by the x minus 5. Okay. Again, now that I have it in the right order and I've replaced all the variables that are missing by a 0, I have to find out what my k is. So what is my k on this problem? My k is just 5, right? So 5 goes outside my upside down house. What goes in here? My coefficients, just my coefficients. So let's do this. So we have 1, -3, 0, 6. Okay. Now let's go ahead and start with the synthetic division. Bring down my 1. 5 times 1 is 5. So -3 plus 5 is a 2. So 5 times 2 is 10. 0 plus 10 is just 10. 5 times 10 is 50. And 6 plus 50 is 56. Yes? So again, 56 was my remainder. The last number here is always your remainder. Okay? So to write the polynomial from our synthetic division, again, we lost a degree. We had a degree of 3. Now we have x squared plus the 2x plus the 10 was my constant, and the last one is my remainder, so it's plus 56 divided by my divisor, which is x minus 5. Okay? All right, now let's look at this concept of the remainder theorem. And what the remainder theorem says is that if I can put a k value into my function, that is going to give me the remainder. And this is very useful, another tool to bypass synthetic division, just to want to make sure if the polynomial that we're dividing is going to give us a 0, we can use this theorem so we don't have to go through even the synthetic division to find out if we're going to get a remainder or 0. Because if we get a remainder, that means that that polynomial wasn't divisible by that polynomial and we didn't really simplify it. Okay, so again, it's all about finding our zeros of polynomials or making our life better. Okay, so let me give you an example of what I mean on how to use the remainder theorem and synthetic division to find function values. Okay, so for instance, I want to find out if 1, and again, this would be my k, if 1, what happens when I plug in 1 to this function, and if I get a number, that means that that's the remainder. Now, if my answer is 0, then that means that this value here is a k value is completely divisible with this dividend. Okay, so let's try it. First, let's do the division so you can see what I'm talking about. Okay, I'm gonna do synthetic division, so I'm gonna grab my coefficients. I have 2. I'm missing the square, so I have to put a 0. Minus 7 with a constant 2. Again, they said f of 1, so this is my k value. K is 1. Let's do the synthetic division. We bring down the 2. Multiply 0 plus 2 is 2. 1 times 2 is 2. Minus 7 plus 2 is minus 5. 1 times a minus 5 is a minus 5. And 2 minus 5 is a negative 3. This was my remainder. But check it out. Let's see what happens when I plug it into the quadratic, right? Or to the cubic. When I plug in this value, into this function, I'm going to see that this k1 was not a zero of this polynomial because I got a remainder. So when I plug it into the polynomial, okay, using the remainder theorem, here if I have everywhere I see x, I'm going to plug in 1. So we have 1 cubed is just 1. Um, 1 times 2 is 2. A negative 7 times 1 is a negative 7. So 2 minus 7 plus 2 is a negative 3. See? The remainder that I got from synthetic division was taken by the evaluation of that k value into the polynomial. So that's why it's called the remainder theorem, because by putting in the k back into the function, it tells you what the remainder is. Okay, so this by having not a value of 0 for the remainder means that this polynomial is, or this k value is not a 0 of the polynomial. Okay, so let's see here. Let's do, sorry. So let's do the B. I wanted to get ahead of myself. So we have a B. Let's do synthetic division for this k value of negative 2. Again, do the same process. You notice that I have now a remainder of 0 for the synthetic division. So what this is telling me that this k value is a factor that is divisible by this dividend. And again, we find out that it's a 0 of a polynomial. That this is a value that our graph crosses the x-axis or is a solution of our answers. Right? All these mean the same thing. And let's use our remainder theorem to show you how it can help us. So if we tried it before we did the synthetic division, if we used our remainder theorem to find out if that k value, the negative 2, was a 0 of our polynomial, we plug it into the function. Everywhere I see x again, I'm going to plug in that negative 2. And you see here that I get, again, these are typos. These should all be negative 2s, okay? I see that my answer is 0, okay? So just, again, this is another helpful thing to help us save some time, especially if you're on a test and you want to find out, you want to simplify a polynomial, you can use your remainder theorem before you can actually come up with the polynomial that's going to give you the answer for the reduction. Okay. All right. So again, how does synthetic division help us solve equations? Well, again, I keep mentioning this process that it's going to help us find the zeros of the function. So if we are given that x is equal to negative 2 is a 0 of this polynomial 2x cubed minus 7x, then I can use this information. I'll do synthetic division to make that polynomial, because that polynomial that's a cube polynomial, it'd be hard to factor or simplify. But if I make it into a quadratic, again, I have formulas that can help me find the zeros for a quadratic, right? So let's do it. Let's use synthetic division to help us do that. I already know that negative 2 is a 0. So the fact that I know that negative 2 is a 0, that is that when I do synthetic division for this polynomial, I am going to get a remainder of 0. So again, if you do the synthetic division and you end up that the remainder is not 0, something went wrong, okay? If they tell us that this is a 0, our remainder has to be 0, okay? It's completely divisible. And here, and when we did it, if I did synthetic division, my k is negative 2, I see that my remainder is 0. Now, why was this useful? Because my quotient now, this 2, negative 4, 1, my coefficients, they're my quotient is now this answer, 2x squared minus 4x plus 1. So now that we see that we have a quadratic, and again, we can factor it, we can do the square root property, or we can use our quadratic formula that always works to solve for zeros. So now, if we use factoring, I like to use factoring all the time. So if it's factorable, I'm going to use factoring by grouping, and I see that I'm able to solve the two zeros, right? And this makes sense. I have a cubic function. I have three zeros. I have 1/2. This is a double zero. and that -2. And we know what this means. This means that our graph at 1/2 only touched. It touched and then went back, right? This -2 tells us that it actually crossed our graph. Okay? And that was from our previous session, right? So these are our zeros, -2, 1/2, and 1/2. Again, 1/2 has a multiplicity of 2. Okay? All right, so let's look at this one. For example, if we had x squared plus 1, okay, if we try to solve for the x on this one, um, we would see that we would subtract 1 on both sides, and we would take the square root of both sides. And up till now, whenever you had the square root of -1, you would answer on your homework does not exist, or this is not a real solution, okay? But now what we want to introduce is this concept of complex numbers, okay? Now for us, from now on, a square root with a -1 is going to have some meaning. Now it's not going to be no more does not exist, okay? Now we're going to put something behind it. We say that this number is an imaginary number, okay? But so you can get an idea of what we're solving. If I had this parabola here that's above the x-axis, or this parabola over here that is below the x-axis, okay? You see that both of these two parabolas are not crossing the x-axis. So again, if you remember from this parabola here, this x squared plus 1, it got shifted, right? 1 unit up, right? So it's not crossing the x-axis. So algebraically, math is telling us, hey, we have no solutions because the graph is not crossing the x-axis, and that's what the solutions are. We're always wanting to find where in our graph it's crossing the x-axis, our x-intercepts, or our solutions, or our zeros. And we see that both of these two graphs, as examples of these two graphs, um, we're going to see that they're not crossing. That's why we would get errors or saying, hey, this does not exist because they don't, right? But now we know that the parabola exists, right? So that's why we use this notation. Whenever we have the square root of -1, we're going to say that it's an imaginary unit. And the variable that we're going to show that it's imaginary is I. So the definition of I is that the square root of -1. Now, if I had I squared, that means that I would square this square, and again, it becomes 1. You guys like to say that it cancels, but I squared would be the -1. So knowing these two things are going to help us write our complex numbers in what's called standard form, okay? The standard form of a complex number is always written in this format: a plus bi, where a is the real part and the bi is the imaginary part, okay? So a complex number is not a hard number. It's a number that's made out of with a real number with an imaginary number. And that's what a complex number is, okay? All right. So again, this is your book definition of a complex number. A complex number is not a real number. It's an imaginary part. And again, this imaginary part was taken when we took the square root of a number that was negative. Okay. All right. So what we're first going to do is let's do some basic operations with complex numbers. So we're going to add and subtract complex numbers. So again, the 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 instructions to do this is very easy. To add two complex numbers, all you have to do is add the real with the real and the imaginary with the imaginary. Okay? And that's how you have to do this basic operation of adding complex numbers. Same thing, the subtraction or difference of complex numbers. The way you're going to subtract two complex numbers is subtract the real with the real with the imaginary with the imaginary. Okay. So again, best way to see these is with examples. So let's look at these. Perform the operations and write the answer in standard form. So be careful, okay? Sometimes they won't give things in the right order, but when you when you do the operations and when you put them in on your homework, make sure they're always in standard form. Standard form means real plus imaginary or real minus imaginary. Okay, so let's look at A. Okay, we have these two complex numbers. Why are they complex numbers? Because I have a real part with an imaginary part. Real part, imaginary part. So to do the first one, again, it's the real plus real, imaginary plus imaginary. So here, the for this first complex number, the real part is 3. The second one is 6, so I'm going to add those two numbers, and then I'm going to add the imaginary parts. I have a 1 here, and I have a 5 here, so 1 plus 5. So when I do this, 3 plus 6 is 9, 1 plus 5 is 6, and again, this has a 6i. So the answer for the addition of these two complex numbers is 9 plus 6i. And if I followed my formula, right, for adding, I see that it gives me the answer in standard form. I don't have to worry about it. Real plus imaginary. All right, let's do B. Um, or let me show you a different method of doing this problem. Again, we could have put them all in a row, right? Since it's addition, I can drop the parentheses because the addition, there's nothing for me to distribute. So I could have just written the 3 plus I plus 6 plus 5i, and then what I do is combine like terms. But again, you got to be careful on this one because since you're combining like terms, you got to make sure that you put your answer in standard form. Means the real part first and then the imaginary. And I would just do that. The 3 plus 6 gives me the 9. The 1 plus 5i, or the 1i plus 5i gives me the 6i. Okay, so this is the second method that you can use to solve it. But again, if you follow the definition format, you'll never go wrong as far as it being in standard form. All right, so let's go ahead and do the subtraction. I want to subtract these two complex numbers. Again, using the definition, I'm going to subtract the real with the real. So 3 minus 2 subtracted with the imaginary part, negative 1 minus a 1. So here, the 3 minus 2 is easy. 3 minus 2 is 1. A negative times a negative is a positive. So negative 1 plus 1 is going to give me 0i. Okay, so be careful. That depending, especially when you're doing your exams with your instructor might always want you to write the answer like this, always in standard form. You have to show the real part and you have to show the imaginary. So the answer would be 1 plus 0i. But if you're doing homework on the computer, if you put it like this or you just put the 1, it will give you the right answer, okay? You wouldn't have to put the 0i on the computer. But check with your teachers, okay? They might always want to see this first one. And it's always a good habit to always write it like this. That way you never forget that a standard form is always real plus imaginary. Okay. And again, using the second method, you see that the minus I plus I got eliminated. They canceled out, just leaving you with a 3 minus 2, which is the 1. Okay. All right. Let's do this one. Oh, and I don't like this one. Okay. Um, so if you see here, you're going to say to yourself, hey, there aren't any complex numbers in here, but we do, right? Because we see here that we have the square root of negative 8. And we know that when we have a negative inside the radical, that's going to produce our imaginary term, right? That I term that we've been dealing with. So on this one, it requires a little bit of work. We need to evaluate these square roots in order to get it into our correct complex form, okay? So let's look at this first. So what I do here is I separate my radical. Let's look at the square root of negative 8 first. I can separate this number inside the radical in this form, negative 1 times 8. That's going to give me negative 8. And the reason why I do it is because I can separate this into two radicals. Let me see if I have it here. Or let me just put it here. I know that the square root of negative 1, okay, is just a I value, right? Or I can use the formula that says that um, -1 is I squared, right? Whichever one you want to think about it. Okay, you can use the first definition or the second definition. But if I'm using the second definition and if I'm evaluating this, I'm going to get with this, right? I simplify this with the I squared with the square. We cancel out the square, or it becomes 1. That goes outside the radical, and that just leaves me with the square root of 8. Okay, same thing with the other one, right? I have the -56. I separated it into two numbers, -1 times 56. I replace -1 with I squared, okay? And then I evaluate the square root. The I squared becomes 1 with the square root, leaving it outside with the I, and inside I have the 56, okay? But now, these two terms are not the same, okay? We need to simplify them. So what we can do is we can simplify the 8. 8 is a product, again, separating the numbers. 8 is a product of 4 times 2, okay? 56 is a product of 4 times 14, okay? I can simplify these because the square root of 4 is 2. So that 2 goes out and I have a remainder of 2 in here. The 4 becomes, again, 2 outside, and I leave a 14. So now this is the answer that the computer will want to see, okay? Um, in standard form, real plus imaginary. Since I cannot combine these two radicals together, I cannot add them together because they're two different ones. One's a radical of 2, one's a radical of 14. So to have it in standard form, I'm just going to factor out the I, and it's okay. Some people like to put the I at the end so you can see it in standard form, but the computer doesn't mind if you put the I in the front or in the back, okay? So you see here's my real part is 2, and my imaginary part is the 2 square roots of 2 minus 2 square roots of 14. Okay. All right. Um, now let's look at this one. Let's look at the product of two complex numbers. So the way we're going to do the product of complex numbers is just the way you've been doing products of polynomials. Okay, we're going to do FOIL on this one. So to do this product of these two complex numbers, again, you're going to multiply the first one with the first one, the first one with the second one with the first, and the second one with the last. Yes? So when I do this, 1 times 8 is 8. 1 times a -7i is a -7i. Excuse me. Now the I times 8 is positive 8i, and the I times a -7i is a -7i squared. Let's go ahead and simplify. The first thing we can do is we can combine like terms, right? We have a -7i plus 8i. That's just going to give me an I, okay? And then here I can simplify the I squared. Oh, I know that I squared, and I put the formula here. I squared is equal to -1, which is what I was using in the previous example, right? So I replace the I squared with a -1. So now I can simplify even further. I can do this product. -7 times a -1. A negative times a negative is a positive, and 7 times 1 is 7. So I have 8 plus I plus 7. Let's combine our like terms again. I have 8 plus 7 is 15. Write this in standard form. Real plus imaginary. I have a real part, which is 15. My imaginary part is just 1 or 1/9. Okay? And this is how I do the product of complex numbers. Okay. All right. So let's have one that I have a complex number that is just I with a complex number that has a real imaginary. This one's no different. All I'm doing, this one's not full. This is just a distribution of the 17i to this complex number. So again, when I distribute the 17i times 1 is a 17i. 17i times a -7i is a -119i squared. Again, I squared is -1, so I'm going to replace it. So a negative times a negative is a positive. But again, please do not put this on the computer or on the test. You're going to get it wrong because it's not in standard form. Standard form is real plus imaginary. So flip it. So I have 119 plus 17i. This is the way the computer wants it and how your instructor wants to see it. Yes? Okay. All right, that is in standard form. All right, now let's deal with division of of complex numbers. Okay, so if you remember, or just to review, when dividing fractions, there's no such thing as dividing fractions, right? We only know multiplication. So to do a division of fractions, you have to multiply the fraction by the reciprocal of the denominator, right? And that you can do. We have the same process when, or similar process when dealing with division of complex numbers. What we need to do is there's no such thing as division of complex numbers, but there is multiplication. You saw me do it. We multiplied two complex numbers together. So what we gotta do is we gotta take the denominator and multiply it by its opposite. Now, this doesn't have a reciprocal. It has another name for the opposite of this. The opposite of the denominator of this guy is called its conjugate. And the conjugate of the denominator is very easy to determine. This complex number is 5 minus 6i. Its conjugate is just 5 plus 6i. All you have to do is change the operation between the two, the real and the imaginary. So if this would have been a plus, the conjugate would have been 5 minus 6i. So again, the conjugate of this one is 5 plus 6i, okay? So now what we're going to do is we're going to multiply both the denominator and the numerator by this conjugate. Again, we can't change the problem, and we need to multiply always by 1, right? So 5 plus 6i plus over 5 plus 6i, that's like multiplying by 1, yes? So again, whatever I do on the bottom, I have to do to the top. So let's do this. This I can do, or we can do. A product of two complex numbers. The first one is easy. It's just a distribution, right? I'm multiplying 3 times the 5 plus 6i, but now I have two complex numbers that are like polynomials, right? We're going to do FOIL on this one, right? So when we do this multiplication, the numerator I get 15 plus 18i. The denominator after FOIL I get 25 plus 30i minus 30i minus 36i. We can combine our like terms. These two become 0. I squared, we know that's negative 1. So let's replace that. And then we have this. 25 plus 36 is 61. You see that when we multiply a complex number by its conjugate, we get rid of the imaginary part. We no longer have an imaginary part on the bottom. We have 61 now. But the top was an imaginary part, right? We have 15 plus 18i. Do not put this on the computer and do not put this on your test for your instructor, okay? We need to have it in standard form. So we separate the fraction here. 15 over 61 will become my real part. 18 over 61, I is my imaginary part, always in standard form, okay? All right, so let's practice just putting things in standard form, okay? Let's say that I want to add these two numbers, the square root of negative 75 plus the square root of negative 12, okay? Again, what I will do first is let me show that I have an imaginary number for these two numbers, yes? So here, again, I separated the negative 75 with a negative 1 times 75 and the negative 12 with a negative 1 times 12. Again, replace the negative 1 with what it means as a symbol, I squared for both, okay? I simplify, the I goes out because I have two of them, so one goes out, leaving me with just a 75 inside for the first one. Again, the I squared becomes I outside only, leaving me with just the square root of 12 inside. And then I'm going to simplify, okay? I'm going to simplify 75. 75 is a product of 25 times 3. 12 is a product of 4 times 3, okay? And I know what the square root of 25 is. The square root of 25 is just 5, so that goes out. I know the square root of 4, the square root of 4 is 2, that goes out. So now on this one, you see that I have a radical of square root of 3, a radical of square root of 3. This means that these two terms are like terms. They are similar. It's like if pretend that the square root of 3 was an x. These two are a single x, So that means that I can add them together. So the way I add this complex number is just the outside with the outside, and I keep the like term, right? So the answer for this one would be 5i plus 2i is 7i with what they are the like, the square root of 3. So the answer of this addition of these two numbers was an addition of a complex numbers, right? Which gave me the 7i square roots of 3. Okay. All right, I have 5 minutes. Again, if I were to write this in standard form, again, the computer will accept that answer, no problem. But again, check with your teacher. Your teacher might always want you to write things in standard form. And the true form of this, and it's a good practice, it would be I don't have a real part, it's 0, but I had the imaginary part, which is a 7i squared roots of 3. Now, one thing that I want to point out too, I'm almost done. The I, we could put it at the end, but the reason why we like to put the I in front and not at the end, especially when we have a square root, is because we can by accident put the I inside the radical, and that would be totally wrong. Okay, so if you do decide to put the I at the end, make sure that you put a space or you get out of the radical before you put the I at the end. Okay, the I, you should never have an I inside of square root. Okay, that would be wrong. So for that reason, that's why they move the I to the front. That way we don't run the risk of by accident putting the I inside the radical. And here, there's no chance that we would do that mistake if we put it in the front. Okay, so that's the reason why you sometimes see the I in front. That's just for us to help us not put it inside the radical. Okay. All right. Now, a great example of now that your answer is not going to be does not exist. Now, when we're solving quadratics, we're always going to have an answer, even though the graph does not cross the x-axis. Now we're going to have imaginary values. So this is a great example. So if you see this quadratic, and if I were to do my quadratic equation to find the solutions of this, again, my a is 1, my b is -2, my c is 2. And if I apply my quadratic, okay, you would notice that inside the radical, I had a -4. Again, chapter 1, this answer would have been does not exist. But now that we're in chapter 2, now this has an answer, okay? This is going to have an imaginary answer. So here, the zeros for this polynomial or quadratic, okay, involve this I symbol, this imaginary. So again, what I did with this -4, I separated into two numbers, -1 times 4. Again, I replaced that -1, or I know that that is going to become an I on the outside. Okay, now I have this answer, but I have two answers. I have a plus or minus the 2i, again, from the formula. So again, I know WebAssign doesn't have the symbol plus or minus, but let me write this as separate, okay? I have two answers. I have 1 plus I and 1 minus I, okay? Now no more does not exist. We're going to get an answer. So this will be the answer for this quadratic. Now in chapter 2, the solution for the x is going to be 1 plus I and 1 minus I, okay? So again, hopefully this presentation helped you. Again, thank you for joining us. In case you're still with us and you want a copy of my presentation, all you have to do is click on the little box here with the arrow on your screen. That will download the presentation for you. In case that you missed it, again, you'll find it on our YouTube channel. Again, thank you for joining me and have a great weekend. I'll pass it now back to our presenters.
Next week, we will have the topic Finding Zeros of Polynomial Functions. Thank you so much to Professor Ruben Carrizales for presenting today. Thank you to the audience for coming and being a wonderful audience, and we hope to see you again soon. Thank you.